All right, so in this video, we're going to be looking at how to solve systems of equations using various strategies on matrices. So we have our first example. We're going to use an augmented matrix in order to solve our system using row operations. So we're going to take our system of equations and we're going to convert it into an augmented matrix. The idea here is, of course, the coefficients of x go into the first column, the coefficients of y go into the second column, and the coefficients of z go into the third column. And then in this example, our final column are the constants. If the coefficient, if the variable is missing, fill it in with a 0, and the signs go with the coefficients. So minus y is -1, for example. So this is our augmented matrix, and now our goal is going to be at a minimum to get this into triangular form, ideally with ones on the diagonal, but at least triangular form, so that our final row is just z equals something, and we can back solve from there, or we can make this left side of the matrix into the identity matrix, and then our solutions we can read directly off of our matrix solution. So let's go through the process. Remember, ideally, we'd like this first entry here to be turned into a 1. And so the way I'm going to do this is I'm going to take R2 minus R1 and put it back in the R1 position. So 4 minus 3 gives me a 1. 1 minus a minus 1 gives me a 2. Minus 1 gives me a -2, and 8 minus 6 gives me a 2. However you get there, that you can get there any way you like. If you'd prefer to divide just by -3, that's fine. Your matrix will obviously look a little different than mine, but you will, as long as you don't make any arithmetic mistakes, you will still get the same answer in the end. Now, once I have this one, I want to use this 1 to get rid of the 4 and the -2. So I'm going to take -4 times R1 and add it to R2 and put that back in place of R2. And then I'm going to take 2 times R1 add it to R3 and put that back in R3. So -4 times R1, this is going to be -4 plus 4 is 0. This gets multiplied by -4, that's -8, plus 1 is -7. This times -4 is +8, and -1 is +7. And then this times -4 is -8, and then added to 8, I get 0. And then in the bottom row, I'm multiplying by 2. So 1 times 2 is 2, added to -2 is 0. 2 times 2 is 4, added to -3 is 1. And then here I get 2 times -2 is -4, added to 1 is -3, and 2 times 2 is 4, added to 10, I get 14. Now, the next thing is I want to make this position equal to 1. And so I could switch these around, or in this case, since everything here is divisible by 7, I'm just going to take 1/7 R2, and I can divide that out. I do want this to be positive, so I am going to switch R2 and R3 because this is already positive and I don't have to change anything. And then I'm just going to divide out that 7. And then the next thing I'm going to do is I'm going to add the new row 1 and row 2 together, or new row 2 and row 3 together, in order to turn the coefficient underneath this one into a 0 also. And so adding those together, 1 and -1 is 0, -3 and 1 is -2, and 14 and 0 is 14. And then I want to turn this position into a 1. So I just keep going down that diagonal, turn it into a 1, everything below it is 0, and I just keep going until I get to the end of the matrix. Here I'm going to divide everything by -1/2, or multiply by -1/2, and I'm going to end up with this as a 1 and this as a -7. Now, once I've gotten to this point, I know that this bottom equation now reads z is equal to -7. and the equation above it reads y minus 3z equals 14. So I could solve for y by substituting in z equals -7, and then if I plug that in, I end up with y is -7. And this top row says x plus 2y minus 2z equals 2. I can plug in the two values that I have for z and y and plug those in, and I find out that x is equal to 2. Now, this form of the matrix is called echelon form, or sometimes row echelon form. In the TI calculator, it's the REF form, which stands for row echelon form. And I would need to back solve it like one row at a time. I have one variable, and I use that variable to solve for all of the other ones. However, this is not where I have to stop. I could continue, as I said, to turn this side of the matrix into an identity. And I would simply do that by, if we go back to the previous line, I'm simply going to use these ones on the diagonal now to, as I did with these zeros down here, to turn everything above them, above those ones, into 0 as well. So I would use this one, and I'd try to eliminate this -3. So I would multiply this row by 3 and then add it to row 2. And then that would get me that -7 down here. I would end up with a row that said 0, 1, 0, -7. And then I would do the same thing up here. I would multiply this row by 2 and add it to row 1. That would turn this into a 0. And then the last step would be to use this one to eliminate whatever ended up being up here, which would still be the 2, and eliminate that. And then whatever this entry came out to over here would be my final answer, which should be x equals 2. So if you continue going through these row operation processes, you should end up with a matrix that looks like this. In your, again, if you're using your TI calculator, this is the RREF form, so reduced echelon form, or reduced row echelon form is why it's 2 R's. Now, we can also solve systems using inverses, assuming our system is invertible. So if we have a matrix equation like this, where we have our A matrix, our coefficient matrix, times our vector of variables, times our constant vector, it can be represented like this, AX equals B. If this, assuming again, it's a simple linear equation, and A has an inverse that we can find, again, either through our calculator or by using that inverse solving process we looked at earlier, then if you multiply both sides of this equation by A inverse on the left, A inverse times A will be the identity matrix, which is like a 1, so it goes away. And then on the other side of the equation, we would have A inverse times B. Now, this is not terribly efficient, because if you have to row reduce A to get A inverse, you might as well just do the row operations on the augmented matrix. But if you have like the formula for the 2x2 matrices, this is a reasonable approach to do, because you don't have to do the row operations. You just have to know that formula. But for a computer, this process is relatively simple. And so you can do this because all of the steps in the process are all buried inside your calculator. And so this will work as long as A has an inverse. If the determinant of A is 0, then you won't be able to get an inverse, and therefore you won't be able to do this. Now, if there is no inverse, then you can solve still by row reducing, but you'll get either inconsistent matrix solution, so there's no solution, or you'll get an infinite solution where you can't quite pin down all 3 variables. One variable is free, and the only way that you can represent that is by doing the row operations we saw in the previous example. Now, if you have an invertible matrix, another way to go about solving the system is using a process called Cramer's rule. Now, this is a very computationally intense process. And so even though we talk about it sort of as an application of determinants in linear algebra, and it is another method for solving systems of equations, it is computationally more intensive because we have to calculate a bunch of determinants. And particularly if the determinants are 3 by 3 or bigger, that process of calculating multiple determinants can be quite messy. But the idea behind Cramer's rule is an interesting one. And so it is one of the processes that we do learn in some classes. Depends on the penchant that your professor has and what's in the syllabus. But let's solve for the y variable in our matrix. The Cramer's rule is nice because it allows you to solve for one variable at a time. You don't have to solve for all of them. You can just solve for one of them. Now, the idea here for each of our variables is we need to calculate the determinant of the coefficient matrix, and then we need another determinant where we are swapping out one of the columns of our matrix with our column of constant vectors. So the process here basically is we're going to find the determinant of our coefficient matrix. And when we go through that process, either by using the calculator or by doing the computation by hand, we end up with this determinant is -14. And then because we're solving for y, that's represented by the second column, we're going to take our constants from our augmented matrix and we're going to stick them inside this coefficient matrix in place of column 2. And then when we calculate the determinant of that, we end up with 98. And it turns out that y is equal to the determinant of this K matrix divided by the determinant of our original coefficient matrix. And 98 divided by -14 is in fact -7, which matches our previous example. So if we wanted to do this for x, the x variable, instead of swapping out the second column of our original coefficient matrix, we would swap out the first column of the original coefficient matrix with 6, 8, 10. So we would have 6, 8, 10 in this first row, and then the rest of these would be the same. If you calculate the determinant of that, then you should end up with -28, because -28 divided by -14 is 2. And then if you wanted to solve for z, again, you would start with your original coefficient matrix, but you would swap out the last column, the z column, for 6, 8, 10. And when you calculated that determinant, you would also get 98. And 98 divided by -14 would also be -7. And so again, you'll get the same answers you got by any of these other processes. But these, again, if you have a 2 by 2 determinants, this isn't that bad. Once you get to 3 by 3 determinants, the only advantage here is that if you only need one of the solutions and not all of the solutions, then you might be able to get there with a little bit less computation. But if you need all of the solutions, honestly, row reducing is going to have fewer operations because calculating those determinants for 3 by 3 matrices or worse, bigger ones, is much harder than just doing the row operation. But it is an option.